Ég ætla bara að byrja. Áður en ég byrja, before we start, this meeting is being recorded, so you online know that. Við erum sem sagt mjög heppin núna að fá fyrirlestur frá glænýjum starfsmanni á Hafrannsóknastofnun, hún Theodoros. Should I try it? The second name? Karpouzogloum. Well, I'm way off, but I did my best. Switching to English now, he's going to talk, give us a talk on the freshwater transport in the Fram Strait. But I politely asked him, because he's brand new in Iceland, to introduce himself a little bit first before he starts. Theo, floor is yours.
Thank you very much. Thank you all for having me here, and it is really nice to be here and present what is basically the work of my PhD, which I finished 1 year ago, roughly. That was done in Tromsø, Norway, in collaboration with the Norwegian Polar Institute and the University of Bergen. This is where I did my PhD. Before that, I was for my master's in the Netherlands, and before that in Greece, where I completed my bachelor's. And now I'm working here as an oceanographer, and I think that that should be it for who am I. And we're gonna talk today more about the freshwater transport in Fram Strait. So this is what my PhD was about. You see a picture from Fram Strait, actually, how it was. I think it was summer 2019. And Sorry?
So online you can't see any slides.
All right.
You either. So maybe cleaner.
I can see the slides online.
Sorry. I'll leave and come back. Continue. Sorry about
that. Hrönn, are you being slow? Or?
Yes, now I can see also the slides.
Perfect. We're back on track. All right, so let the presentation start. So we're gonna talk firstly, we're gonna go through a historical retrospective of oceanography in the Arctic Ocean. Basically, we wanna learn some stuff about the Arctic Ocean first, how our knowledge for the Arctic Ocean evolved through time, and we're going to say some more modern stuff, contemporary understanding for the Arctic Ocean, and research changes in the Arctic Ocean that motivate our study for freshwater transport in Fram Strait. Fram Strait is the gateway connecting between the Arctic Ocean and the Nordic Seas. We're gonna show the material methods used for this study, mention the results, which have been concluded in 3 papers, and finish with the concluding remarks. So we start with the 16th to 17th century. This is when we're getting off what we call the dark times. This is the revolution of science and art, basically, which comes with the Renaissance and the Enlightenment. And we have one man here that we want to exceptionally mention. You might know him as a physicist. Basically, he was a polymath, meaning that he was a physicist, a mathematician, an engineer, and most probably many other stuff. It's Galileo Galilei, an Italian polymath, as we said. We want to talk for him because of his contribution to observational astronomy, and we're mentioning him because we'll be more interested in understanding what observations how observations are important for our understanding of our world. So basically, Galileo Galilei, he invented a better version of the telescope, and with that, he was able to observe several stuff on the night sky: the Milky Way, the Jupiter's moons, the Saturn's rings, the craters of the moon, and the sunspots in the sun. So all these, we saw them firstly because of his invention of the telescope that allowed us to observe the skies, basically. And let's contrast that a bit. You see the date, Galileo Galilei, he was born in 1564, and 5 years after his birth, this map is published for the Arctic Ocean. It is the first circumpolar map showing the Arctic Ocean. And we see this shows a popular narrative at the time, which was basically what it says is that in the middle of the Arctic Ocean there lies a magnetic island. This is why our compasses show the north. Surrounded by a sea, in turn surrounded by 4 continents, divided by 4 rivers. And that was a story that was said by an English Franciscan monk who had claimed to have traveled to the north, seen all this stuff, and then returned to Norway actually, and said this story to the King of Norway. So basically, this is our first understanding of how the Arctic Ocean looked at the same time that we were capable of observing the night sky. We were not capable of observing the Arctic Ocean, and this is why our understanding was so poor at that point. We continue. On the 19th century, there is another map published by Silas Bent, and what it shows is another popular theory at that time, which basically says that the northern intensified currents would carry so much heat and salt into the inner Arctic Ocean that wouldn't allow him to freeze. So basically, many expeditioners and explorers were setting sail to the inner Arctic Ocean to find this supposed open sea, with the result to get trapped in the ice and nobody would see them again. So basically, at the same time, this is the time that Einstein is born, and after 25 years, he gives the theory of relativity. So basically, this is how far in the past, polar oceanography and our understanding of the Arctic Ocean is not so new. The first person to actually travel into the inner Arctic Ocean is Theodoros Nansen. He creates a ship which would be strong enough to maintain the ice formation and not get crushed below the ice. He names his ship Fram, which is the Norwegian word for forward. He sets sails from Tromsø. He takes the northwest passage and northeast passage, and then off the Siberian shelves, he gets the ship into the Arctic Ocean. It freezes, and then with the currents, it travels along the inner Arctic Ocean and exits from this area, which was called after his ship, the Fram Strait. So basically, we want to talk more about the Fram Strait, what this opening between Spitsbergen and Greenland was named. And we're going to be talking about freshwater fluxes through that strait. This was written by Nansen in his publication. The inner Arctic Ocean is a deep ocean covered year-round with sea ice with a warm and salty layer of Atlantic origin water at around 200 meters depth, which is separated from the sea ice by a cold and fresh surface layer of polar waters. So the last polar waters, this is what we'll be interested in. All right, so freshwater in the Arctic Ocean. The sources of freshwater in the Arctic Ocean are 3. It's meteoric, means precipitation, or river runoff. This is the same quality of water. Pacific water, this means that water is coming from the Pacific opening, the Bering Strait. Waters of the Pacific Ocean are fresher than the waters of the Arctic Ocean, so then they are considered as a fresh source. And ice melt water. Circulation in the Arctic Ocean for fresh water is mostly wind-driven. That is because fresh water is light, it resides close to the surface of the ocean, so basically it circulates with the wind-driven circulation. And there are two main characteristics that I want to draw your attention. This is the Beaufort Gyre, which is a big anticyclone positioned in the Canadian side of the Arctic Ocean, where we have most of the fresh water, and we will gonna explain why. And we have the transpolar drift as well. This is actually the current that Nansen's ship followed from the Siberian shelves to Fram Strait. So that is the circulation of fresh water. And then for the outflow of fresh water occurs from two openings connecting the Arctic Ocean to the Atlantic Ocean, and this is the Canadian Arctic archipelago that you see here, and the Fram Strait that we're going to be talking about. So I want to talk shortly about what we call the Ekman transport, because it's going to be proof useful afterwards. We have high pressures and low pressure systems all over the globe that, I guess you know, this is created by wind. No, this is actually, these results, high and low pressure systems result into wind patterns that they are clockwise or anti-clockwise, as you see here. What I want you to know, and will be useful later, is that in a low pressure system, when the winds are anti-clockwise, we have what we call Ekman transport in the wind-driven layer, so in the layer of the sea that feels the effect of the ocean, that is diverging, so what you see here. And then where we have high pressure system, the layer of the ocean that feels the effect of wind converges. So basically, the reason why we have more fresh water in what we call the Beaufort Gyre is because the Beaufort Gyre is located below what is called the Beaufort high pressure system, resulting into convergence in the upper ocean, which maintains fresh water in the same place. This is again the map of the Arctic Ocean. The color shows the sea level pressure. So you see that with red we have this large area of convergence over the Arctic Ocean. This is the Beaufort Gyre. And then we have a more blue area which extends from here, Iceland, to the north, and what is called the Eurasian side of the Arctic Ocean, including the shelf seas, and which is more dominated by the Icelandic low, and the circulation between those two areas is different. So we said that the circulation in the Arctic Ocean is wind-driven for mostly when we talk about freshwater. And if we want to study the freshwater transport in Fram Strait as it is wind-driven, then we are for mostly interested in local forcing. So what drives the freshwater should for mostly be the local winds. There is another thing that people have been focusing on when we're talking about freshwater transport in Fram Strait. It has been shown that what we call the circulation regimes within the Arctic Ocean is important, because winds affect the velocity, which is one component of transport, but then we want the waters in Fram Strait to be fresh as well, to have high freshwater transport. So there are circulation regimes in the Arctic Ocean that have to do with what we were discussing before about convergence and divergence of freshwater in the Arctic, in the Beaufort Gyre. So we have the cyclonic regime, which you see it here, and that occurs when low sea level pressure and surface layer that spreads fresh water to the periphery and to Fram Strait. And this is when we have lots of fresh water in the Arctic Ocean, in the Fram Strait, I'm sorry. And then the opposite occurs when we have high sea level pressure anomalies that result into convergence of fresh water, so the fresh water cannot escape, let's say, from the Beaufort Gyre and spread to the periphery. So this is what we know for now that should be important for the circulation of fresh water in the Arctic Ocean and the export from Fram Strait. The fresh water exits from the Arctic Ocean, from the Fram Strait, with what we call the East Greenland Current. You see it here. It is on the west side of the strait, while on the east side of the strait we have Atlantic waters entering the Arctic Ocean. Yes, and a part of the Atlantic water is recirculating within the Arctic Ocean, within the Fram Strait, and the two water masses are propagating one next to the other. That gives rise to what we call the baroclinic component of the East Greenland Current, which basically says that there is a gradient of density there, but that's not so important for us now. And the other thing that we should mention now is the vast East Greenland shelf, which is here, that is another candidate for important, for big amounts of fresh water exiting the Arctic Ocean. And we're gonna talk more about it in a while. So future projections, what's gonna happen with fresh water in the Arctic Ocean? The models show that the freshwater content in the Arctic Ocean is expected to increase. Actually, it does increase. We have seen that with observations as well. And it is possible to quantify this change, and it is one of the most prominent changes that we observe globally. And the increase of freshwater content in the Arctic Ocean is expected to result into an increase of the freshwater outflow from Fram Strait, which is expected to affect stratification, the overturning, and marine life in lower latitudes. So basically, this is what we are interested on here in Iceland, while we are just south of Fram Strait. Some observed changes that we have seen already is there was a prominent period of increasing freshwater content, mainly in the region of the Beaufort Gyre that we saw here, and that was between the 2000 and the 2010. And then people were surprised to see that at the same time in Fram Strait we didn't really saw any increase. So basically freshwater was increasing in the center of the Arctic Ocean, but the export was not showing any increase. And then a period of that the Beaufort Gyre plateaued. So basically between 2010 and 2016, the wind forcing over the Beaufort Gyre relaxed, and we had spread of fresh water into the Arctic Ocean, into the periphery, and that was when we saw high freshwater transport in Fram Strait. That was in 2011, 2012. After 2016, the Beaufort Gyre started intensifying again, but the fate of freshwater transport in Fram Strait was unknown. Basically, the data hadn't been analyzed yet. And this is where the project that you're gonna see now comes in, because we want to know what is the freshwater transport in Fram Strait after 2015. We could expect it to see increasing because of the freshening of the Arctic Ocean, or again decreasing because most of the fresh water could be converging into the Beaufort Gyre because of what we were discussing before, because of its intensification. So basically, the research questions that we want to answer with this project is: what is the observed freshwater transport of the East Greenland Current in the Fram Strait post-2015? What is the unobserved freshwater transport over the northeast Greenland shelf? And which are the forcing agents responsible for the variability of freshwater transport on the East Greenland Current? We're gonna follow with the material and methods. We're gonna discuss firstly the Arctic Outflow Observatory. So basically this is the observatory that provided with the data that we have analyzed. Every summer, the Norwegian Polar Institute organizes an expedition in the Fram Strait. You see the map here, and basically the cruise is supposed to collect the moorings, service the moorings, then we take the data, we analyze the data, and of course every other kind of activities that can take place, they do take place on board. So those are some cool pictures from the Fram Strait. And we're going to talk more about the moorings. I worked with the data from the moorings. So you see that the moorings were, the observing system, the Fram Strait Arctic Outflow Observatory was initiated in 1997. Back then, the mooring deployments were fewer, so basically we didn't have that much of a good coverage, while in the course of the years, more money were coming in, so more moorings were coming in, and we were getting a better coverage of the East Greenland Current. And those are the data that we analyzed between 2003 and 2023. Actually, we started in 2003 because that was there was a new mooring on the shelf that resulted into better coverage of the RI. And I'm going to continue now with what do we calculate. So we have been discussing about the freshwater transport. The freshwater transport is basically the equation that you see here. And who is familiar with this equation? Who has seen that before? All right. So basically, I'm gonna keep this part to the minimum. Andreas is raising his hand, of course. Yeah. So basically, though this is the freshwater transport that you see here, and this is the freshwater content, those are called the freshwater fractions. And there has been a lot of discussion in physical oceanography on whether it is meaningful to use this kind of fractions or not. Basically, when I was starting my PhD, I read a summary of a conference, actually. It was a statement, actually, after a certain conference that happened, where a certain researcher was saying that if you are to calculate this kind of fractions, you should just better go for a walk in the sea. There's no point of doing it. So this has been a topic of active, let's say, conversation in the scientific, in the physical oceanography community. So I'll try just to give a rough explanation of what these freshwater fractions are. So basically what we have here is the salinity that we observe. And we are using what we call the reference salinity in these sites. So basically, if we see the numerator, we see that it is a reference salinity subtracting, the observed salinity is subtracted by a reference value, which basically says the salt or excess deficit of a sample relative to a reference value. And then if we divide that, this becomes dimensionless. And then if we integrate then it gets the dimensions of meters. So basically, the freshwater content is the thickness of the freshwater layer. Freshwater we define as the water which is fresher than a certain reference, and if we displace that to a surface, it has a certain thickness. This is what we are trying to calculate. So I think I'm gonna skip this. It could be meaningful for Andreas, who's online, but I think it's not gonna be meaningful for the rest. Let's just say that what we're going to do is that in this project, the problem with using the reference salinity is that there is no right or wrong number for it. So basically, if I would use one value, a researcher that would use a different one could come up with different results, and that could lead into confusion. The value that we used is the mean salinity of the Nordic seas, and this should allow us to investigate the amount of fresh water exiting from the Fram Strait that has the capacity to freshen the Nordic seas. So this is what we're studying, and to explain better the problem, I think that let's just say that As we said, there is no unique value that somebody can use, but what we tried to show, what I tried to show with this, in this work that I did was that although there is no right or wrong, there is a reason for using the reference salinity. And the reason for using the reference salinity is to manage and make the freshwater fractions sensitive to changes of velocity and salinity alike. And I'm going to explain maybe a bit now why. This what we see here, this equation is salt transport. We have inside velocity, salinity, and density. Velocity, salinity, and density. So below you see the volume transport that depends only on the velocity. And if we plot two time series, one next to the other, what we see is this. So basically what you see here is one time series. Black line is monthly values. Red line is 3-month averages. But what I have plotted is two time series. The reason why you don't see the second one is because they completely overlap. You see that they have different axes, different values, so the mean value of the two time series is different, but the anomaly from the mean is completely the same. So what we say is that the salt transport anomaly doesn't depend on salinity changes, and this is a fact, doesn't seem to depend. So basically, if we're calculating the salt transport in the Fram Strait and the salinity in the Fram Strait would increase, we wouldn't see a difference, because salt transport is not sensitive to changes of salinity. And this, if you play a bit with mathematics, you can understand why it is. And it is because the salinity has a much smaller anomaly to mean value ratio than the velocity. This means that when you multiply those quantities, then velocity dominates, velocity anomaly dominates. And velocity anomaly explains 99.8 of the anomaly of salt transport, while because of the use of the reference salinity that we have here in the numerator that decreases the mean value of salinity without altering the anomaly, we end up with freshwater content anomaly and velocity anomaly comparable within the freshwater transport fraction. So basically, whatever you understood, I think. And we continue with the scientific results that should hopefully be more interesting. And the first research question is, what is the observed freshwater transport of the east-diurnal current in the Fram Strait post-2015? Those are the time series that we see here. And what we see is that freshwater transport decreased after 2015, and that was because of a reduction of in the freshwater content, as well as in a reduction on the volume transport. So both variables that we are interested, both salinity and velocity, are decreasing, and we're going to try and understand why. What you see here is the main cross-section of salinity in the area that we are interested, the east-diurnal current, and this is the main cross-section of velocity between the period 2003-2009. So what I'm going to show now is the anomaly from the mean of the period 2016 to 2019. And with blue color here, you have an area which is freshening. This is something that we were sort of expecting. The sea ice is melting. This adds more fresh water in the water column. And this is what we see here with blue color. The upper polar waters are becoming fresher. But then if we go below, we see something different. We see a big layer of waters that they're becoming more saline. This is what you see with the red color. So this results overall into the reduction of the freshwater content in that region. And if we were to try and understand why is that, below the polar waters, we have the Atlantic waters that we said that they are recirculating within the Fram Strait. So basically what it appears that we observe here is an Atlantification of the western side of the Fram Strait. This is what we're discussing in this paper. So we were expecting to see maybe a freshening of the first layers, or maybe freshening in the area of the east-western current, but instead we're getting a salinification. That is because of more Atlantic waters in the water column. And then at the same time, this results into a deceleration of the core of the east-western current, and this is because of the changes that occur into the distribution of the water masses that reduce the baroclinic component of the current. So basically, we conclude on the first paper that the mean freshwater transport of the east-western current in Fram Strait decreased after 2015 due to weaker velocity and increased salinity. And we proceed with the second paper. So what we did now was to calculate the freshwater transport in the area that you see here with the red dots, and those are our moorings. And we want to know how much freshwater is passing from the right side of the moorings. So basically the arrow that you see here. So how much freshwater could we be missing from our estimations? And basically this is quite difficult because we don't have observations there. So basically, what we try to do is to use any kind of observations that we have in order to get the best estimate that we can get. So basically, we're using summer CDD sections that they're repeating every September between 2013 and 2021. That they don't reach to the coast of Greenland, but just to a certain extent, and that is because of permanent sea ice that doesn't allow us to go until the Greenland coast with a ship. We use new mooring deployments in the area of the shelf, and additionally we're using RF5 winds and dynamical ocean topography. And basically our I'm gonna show you two estimates roughly. What we're doing is, first of all, we find that there is a good correlation between the winds and volume transport. So correlation is 0.97. So that could be promising. So we calculate volume transport based from the actual wind data. We come up with an estimate of the volume transport. And then we want to come up with an estimate of the freshwater content. And for that, we're using the summer cruises that we had and some occasional spring cruises. So basically, we are having a very rough estimate of freshwater content seasonality only from two values. And this gives us the freshwater transport and an estimate of freshwater transport, which is actually 40% of the total in Fram Strait. So basically, that's a big number. We do the same in a different method. We use dynamical ocean topography data to calculate the surface currents. And from the salinity, so the freshwater transport, freshwater content seasonality, we calculate the geostrophic velocity seasonality as well. We reference the geostrophic velocity to the surface salinity that we calculated before. We get a seasonality for volume transport, and from this we're getting the freshwater transport, getting a new number, which is 45%. So again, what we show is that two methods with very high uncertainties, actually the uncertainty in both methods was as large as 100%, point to the fact that half of the freshwater transport in Fram Strait can occur from the shelf. So we are mentioning here that it would be interesting, it would be important to try and observe this part of the ocean. So basically, year-round freshwater transport of the shelf is estimated to 52 millisvertrap, or 43 of the total freshwater transport from the Fram Strait. And then we continue with the third paper. We want to answer which are the forcing agents responsible for the variability of freshwater transport in the East Greenland current. So we start again with the time series that we saw before. Volume transport, freshwater content, freshwater transport. And we want to explain the variability that we see within this time series in interannual timescales mostly. We're using additional data, sea level pressure and winds from the ERA5 dataset, and we're using dynamical ocean topography from a dataset published by Armitage et al. We're not going to show this last one. And the process is very simple. Every time series are getting deseasoned, we calculate correlation maps. So basically that is what is the correlation of our time series with the individual grid cells that we have our additional data, the sea level pressure and velocity. And something to remember, so basically this is what we were discussing before. We want to know why our time series vary in the way that we see. So basically, we want to know what forces the variability of freshwater transport in Fram Strait. We discussed two things: local forcing. So basically, we're interested in the winds, and at the same time, large-scale sea level pressure patterns that allow the release or not of fresh water from the Arctic Ocean that can spread or not to the Fram Strait. So if we remember this, we continue. And this is our analysis for the volume transport. Volume transport seems to show whatever we saw here is significant correlations. So basically, what we saw here is that volume transport appears concurrently at the same time with a low pressure system over the Barents Sea. Whenever we have strong volume transport in Fram Strait, a low pressure system dominates the Barents Sea, resulting into a cyclonic circulation around the low pressure system, resulting into northerly winds in Fram Strait, resulting into southward transport of fresh water. So basically, Fram Strait local winds force instant southward volume transport. This is our first result. And now things become more complicated for the freshwater content. So basically what we do firstly is we want to know, all right, what is the concurrent correlation between freshwater content and sea level pressure in the Arctic Ocean? There is none. So basically, at the same time that freshwater content is high in the Fram Strait, nothing happens in the Arctic Ocean. So we want to know what happens before. And if we calculate the lagged correlation from 0 to 24 months, we start seeing some interesting patterns. So in the first 9 months, before high freshwater transport events in Fram Strait, low pressure systems dominate the Arctic Ocean, and this is what you see here. And then in a period 13 to 24 months before, high pressure systems dominate the ocean. The first one is familiar, is the circulation regimes that we discussed before. The second one is new, and we're going to try to understand it. But what we're going to do now is we're going to average sea level pressure within this period, so basically 0 to 9 months before the occurrence of freshwater content in the Fram Strait, and 13 to 24 months before, and we're going to see the results. The first one is this one. So basically 0 to 9 months before of high freshwater content in the Fram Strait, low sea level pressure anomalies and cyclonic wind anomalies dominate the central Arctic Ocean. This is the anti-correlation that you see here. So basically what are we seeing here is that you remember the circulation regimes that we discussed before. When the Arctic Ocean falls into a cyclonic regime, then the wind-driven convergence in the central Arctic Ocean decreases, so fresh water is allowed to spread to the periphery, and then we see it in Fram Strait after 0 to 9 months. This is the storyline here, and this is not something new. This is something that we sort of expected. What is more new, maybe, is this one. So basically, this shows something different. 1 to 2 years before the occurrence of high freshwater content in Fram Strait, the Eurasian side of the Arctic Ocean falls into an anticyclonic state. So basically, we see convergence in the Eurasian side of the Arctic Ocean. Although this is new, this is not completely new. There was a paper from an Alexandra Yan, who's a modeler, a physical oceanographer in the United States. And basically in modeling and analysis of fresh water in Fram Strait, they showed that 2 years before we see high freshwater content in Fram Strait, high pressure systems in the Eurasian side of the Arctic Ocean can result into sucking freshwater from the shelves. So most of the freshwater reside in the Eurasian side reside on the shelves. So basically high pressure systems would allow them to enter to the deep basins, and then with the transpolar drift after 2 years they would arrive in Fram Strait. So basically this is what we believe that we see with this third mechanism. And all right, we saw volume transport, we saw freshwater content. We'll do the same for freshwater transport, and we hope to see the same, and indeed we see similar patterns. So basically we named 3 forcing agents that drive freshwater transport in Fram Strait. First, we named the North Pole convergence, and that says that 1 to 2 years prior to high freshwater transport, converging anomalies in the Eurasian Arctic freshen the reservoirs north of Fram Strait, preconditioning fresh outflow events. The second one, we name it the Beaufort gyre weakening, which says that 0 to 9 months prior to high freshwater transport, diverging anomalies in the southern Arctic direct freshwater to the emergence of the ocean and to Fram Strait. And then the third one is the more easy to understand and the one that we were expecting, that Fram Strait northerlies force southward volume transport on the same month. So basically this concludes the third paper for this study. Fram Strait local winds force eastern southward volume and freshwater transport, and Arctic Ocean large-scale wind variability forces 2 distinguished lagged responses of freshwater content and transport in Fram Strait. And concluding remarks from the first paper, we got the mean freshwater transport of the EGC in Fram Strait decreased after 2015 due to weaker velocity and increased salinity. Year-round freshwater transport over the shelf is estimated to be 52 millivertrap, or 43% of the total freshwater transport from the Fram Strait. And the Fram Strait local winds force east and southward volume transport and freshwater transport, and Arctic Ocean large-scale wind variability forces 2 distinguished lagged responses of freshwater content and transport in Fram Strait. So that was the presentation, and the floor is open for questions.
That we simply use not the speakers, microphones in the ceiling. We just have to talk loud.
I'll try my best. Thank you for the talk, Theo. Very interesting. So, with regards to the last paper, are these 3 forces? Do they all have to take place together?
So basically this is this figure. Whenever you see purple, it's North Pole convergence driving the freshwater transport events. Whenever you see yellow, it is the Beaufort gyre weakening. Whenever you see red, it's Fram Strait winds, basically. Yes.
One of them takes
Yes.
place, then you will see increased freshwater.
You can, yes, exactly.
And they are like, is there any connection between these 3 events?
Yes. So basically, correlation between the 3, I don't know, but then at the same time, what we're doing is we calculated 3 indexes that sort of describe what really happens. So basically, it's not that sea level pressure drops only in the Beaufort Gyre or sea level rises only in the Eurasian Basin. It can be a mixture. So basically, if the Beaufort Gyre moves from the Canada Basin to the Eurasian side, which had happened before. So basically, the reason to see these events here, let me show with the cursor. So basically, those high freshwater transport events, they were because the Beaufort Gyre moved from the Canadian side to the Eurasian side. This resulted into drop of sea level pressure in the Canadian side and increase of sea level pressure in the Eurasian side. So basically, with just one movement of the gyre, we saw both the mechanisms activating. And this is why we saw these high freshwater transport events in Fram Strait here.
Online is next.
Yeah, I have one question about the predictability or using these results to try to predict the freshwater transport through Fram Strait.
Yeah.
Are you sure you can do that? Because that would be very interesting for us if you could say, like, there is going to be a big freshwater flux in next year or something like that.
I'm sure that I cannot say that I'm sure that I can do it because I haven't done it. So basically, something that I haven't showed is this. This is correlation of freshwater transport and volume transport with indices that can more or less be predictable. So basically, we see that freshwater transport, which is on top, here. Well, we're using two indices. This is the Arctic Ocean oscillation that has to do with variations within the Beaufort Gyre, and then freshwater transport doesn't show any correlation with that. But we see what is very interesting is that we see a lagged correlation with the Arctic oscillation. The Arctic oscillation is something that has to do more with what happens in the Eurasian side of the Arctic Ocean. So basically, when we have low pressure systems coming from Iceland, from here to the Eurasian side of to Barents Sea, let's say, we have positive phases, if I'm not mistaken, of the Arctic oscillation. Regardless, what we see is a one year lagged anti-correlation with the Arctic oscillation, which means that whenever we have a low index for the Arctic oscillation, negative index, positive index, 1 year later, usually we get high freshwater transport. So that could be actually something to start from. And we can explain why this happens. It is the third mechanism. So basically, high pressure systems or high pressure anomalies in the Eurasian side of the Arctic Ocean results into is basically a positive AO index, and that results into convergence of freshwater in the Eurasian side that the next year or years is transported from Fram Strait. So I would start with something like this.
Okay, thank you.
Covered? Yeah. Yes, Andreas? Andreas, can you hear us?
Sorry. Can you hear me?
Yes.
Yeah. Okay. Yeah, thank you very much for the very interesting talk. There was one thing what I wondered about is, so it is in the sections in Fram Strait, it was very evident that the sort of Atlantic water is extending further onto the shelf, and so that the cross-section area of the freshwater is much smaller than it used to be in earlier years. Yeah, do you have any explanation on why is this actually happening? Or
Yes. No, I don't have a good explanation for that. So we have been discussing on this. We don't know. So basically, we see more Atlantic waters. We don't know, firstly, if those are Atlantic waters recirculating from within the Arctic Ocean, or so coming from the transpolar drift, or if it is Atlantic waters that they had recirculated just north of Fram Strait, resulting into what we see here. And a tracer's analysis would be interested from that perspective, but it hasn't been done yet. So basically, there are two possible explanations. One is that basically it is the retreat of the polar waters that are coming from the Arctic Ocean that allows the spreading of the Atlantic water, or it is that it is an intensified wind pattern that results into more recirculation of Atlantic waters locally that then would limit sort of the polar waters coming from the Arctic Ocean. I think this is one of the points that we couldn't really explain why we see more Atlantic waters in the Western Fram Strait.
Yeah, thank you.
So anybody from the hall? Any questions? And Fram is done next, and then you guys here in the front.
Next. Thanks a lot. It was really informative and a really good presentation for a non-physical oceanographer. My thoughts are about what's the implication of all of this? What does it mean that you have more or less freshwater inflow from the Fram Strait into the Nordic seas? And I guess there's 2 points that I'm thinking about. What is do we know what the impact on the ecosystems in this region are? And then, there's always discussion about the AMOC on the other hand. Do you have some words on that?
Yeah, so basically for the first part, I guess I have been contacted by people studying the Icelandic capelin, basically, and I have been told that there appears to be a correlation on the stocks here and the amount of fresh water that is present in the area. Of course, this is something that I don't know by myself. This is what I have been told. And then these people were interested to know more about the freshwater transport in Fram Strait, because that should give some predictability on the stocks of Icelandic capelin. So that is one. And then on what you mentioned for the AMOC, basically, maybe what is worth mentioning is, I don't know who of you have seen one paper from this is from a working group in the Netherlands, from Utrecht University. They have published recently a paper that basically shows what would be the results of a shutdown of the AMOC in a climate model. And they had shown that Reykjavik mean temperature, the mean temperature in Reykjavik would drop to minus 13, if I'm not mistaken. So basically, not a very pleasant perspective. What could be interested to be brought into perspective is that the way to force this model in order to result into a shutdown of the meridional overturning circulation was with freshwater transport that was equivalent to every year having to double up the amount of freshwater exported from Fram Strait. So the fact that after 2015 we see a drop, this is something that could be understood as well, we don't need to get, on the boat already to travel to the mainland. So yes, that would be my comment.
Came here, we don't want to lose you right away, so good to know.
Who of you wants to do first?
Thank you, Theo, for an interesting presentation. Do you know how the variation in the outflow, if it impacts summer sea ice on the east coast of Greenland and in the Greenland Strait? There's high variability in the summer ice there. I'm just wondering if that's one of the factors that impacts it.
I can imagine, but I haven't looked at it at all. So no, I don't know. You mean on the East Greenland shelf, downstream from Fram Strait?
Yes.
Yes.
So where the current is going.
Let me just say that what we have been discussing is quite different from what is happening with sea ice. So basically, sea ice is doing a completely different thing. Sea ice in the Fram Strait has been mostly, or largely actually, decreasing. We see no changes in Fram Strait, liquid freshwater transport. We see high variability, but sea ice is mostly dropping, and yeah, the minimum was in 2018, and I think that it continues dropping since. But yeah, no, what ice is doing in Fram Strait is different than what liquid freshwater does, and I would expect the first one to be more related with sea ice concentration downstream.
Because we've been seeing more and more in the July survey in recent years than we used to.
More.
It's quite surprising,
Yeah.
so I was wondering if there was wondering why.
Yeah, I don't know, but there is, big part of Greenland in the middle as well. So I don't know the sea ice composition here north of Iceland, and how much it is because of export from Strait, or if it is because of ice coming into the current from Greenland. Yeah, I don't either. Sorry.
Jonas, you're the owner of the last question, the seminar. We better be good.
Thank you. I just had one question, so back in the days, our oceanographers, were discussing the great salinity anomaly, and, which occurred in the 60s, and then another one in the late 70s. And just your comment on that, regard, now you're, the salinity, the freshwater coming from the Fram Strait at that time, causing kind of sea ice, the Havis out in Iceland,
The ice years.
The ice year in Iceland, that somebody might remember, I don't.
Yeah. So basically, I think, first of all, I haven't read much about the salinity anomalies. That was a bit more in the past than my area of focus. I think that it was supposed to have exited from Fram Strait, but from the Canadian Arctic archipelago as well. Of course, if you saw it here in Iceland, then this means that that must have been the effect of waters coming out from Fram Strait. I cannot really say much. The only thing that I could say is that apparently the period of high freshwater transport in Fram Strait, that was between 2010 and 2012, 13, apparently hasn't really affected your climate. So it might be that the signals coming from the south might be, sort of counteracting. But yeah, I'm sorry, I don't know. And that's it.
Time's up. So I would like to thank Theodoros for a very interesting talk, and for you coming here. Thank you.
So